Okay. Okay. So at first, let's see what we covered in our last class. So first of all, we okay. So we learned about BJT. So BJT is a three-terminal reverse. Okay. So that is our base, collector, emitter, and then it has got two junction, emitter to base junction and collector to base junction. So that is our uh, emitter to base junction. And if you represent it in terms of two diode model, it's like that. Emitter, base, collector. That is an emitter to base junction, and that is our collector to base junction. So, so then we learned that if since we have two PN junction connected back to back, if you want to bias both the both the uh, PN junction diode at the same time, which means emitter to base junction and collector to base junction. So we can do it four ways. So we can make emitter to base junction forward biased and also collector to base junction forward biased. That is one possibility, which we learn that it is called saturation region. And then if we make emitter to base junction reverse biased, a collector to base junction reverse biased, that is also another possibility, which we called a cutoff region. And then emitter to base junction, we made it forward biased, and collector to base junction, we made it reverse biased. We said that this combination leads to the forward active region. And then finally, if we make emitter to base junction reverse biased and the collector to base junction forward biased, we said that it is reverse active region. And generally, we said that the emitter BJT is not biased to operate in the reverse active region. So if this is the case, then we learn what happens if emitter to base junction is forward biased and collector to base junction is for reverse biased. For example, like this one. Okay, so we apply a voltage such that this emitter to base junction, we apply a voltage VBE such that it is forward bias. That means so it's our NPN BJT. So NPN. So if you want to make it forward bias, P side is higher potential, N side is lower potential. And if it is make it reverse bias such that VCB, so plus minus. So N side is connected to the positive terminal and P side is connected to the negative terminal, reverse bias. Okay, and here, so we, in that case, it is in active region. Active region. If it is the case, then we have three current flowing: collector current, of course, entering the BJT, base current entering the BJT, and emitter current entering the BJT. And then we found out in that case, all the current components depends only on one thing, that is VBE. So if you change VBE, we found out that we have base current changing, collector current changing, emitter current changes. So we can write it this way: say IB or IC or IE. All of them are proportional to e to the power VBE over VT. So which means that if you change VBE, you get change IE, IC, IB. So that is actually a diode characteristic. So here you can say it's a diode. So if you apply the voltage here, VBE, okay, so plus, minus, and VCB plus, minus, and the current is IE, IB, and IC. All of them are dependent on VBE. So it is diode current. If it is a diode current, when it is forward biased, we know the diode IV characteristic looks like this. Okay. So it's a diode IV characteristics. Whether it is IB or IC or IE, and the voltage is VBE. So
স্যার,
IV voltage
মিটিং এ
VBE.
কয়েকজন ঢুকতে চাচ্ছে, ঢুকতে
Yes,
পারতেছে।
yes, I know. Let them wait. Let them wait. I am not going to go back and forth. I know when I'm going to let them in. Okay, they should be. I have started the class exactly 33 past time, so it's not possible for me, and it's not appropriate for me and for the rest of the student to going back and forth and let them in. So I know when I'm going to let them in. Is that understood?
ইয়েস স্যার।
So since it's a diode, so diode characteristics such as exponential curve. So that means as you are changing VBE, you have base current changing, also collector current changing, also emitter current is changing. All right. So particularly interesting is the fact about IC. IC. Of course, IC, we have, as we said, e to the power VBE over VT, and most importantly, independent of VCB for VCB greater than minus 0.4 volt. So we said that it doesn't matter if you're changing, if you're changing VCB, you're changing VCB for VCB, you're changing VCB, but IC unchanged. Okay, IC unchanged. So that can be graphically represented. Okay, if I want to represent this statement graphically, it looks like this. IC and VCB. So that is our 0. Okay, and then we found that it looks like this. So that is minus 0.4 volt. So for remain unchanged. So for VCB greater than minus 0.4 volt, it is constant, unchanged. You are changing VCB, but what is the value of current? If it's, you see, current doesn't change. On the other hand, so less than VCB, less than VCB, we're going to find out is like that. So it's minus 0.7 volt. So we said that if you look at the characteristics of the curve, it is quite familiar for us. Okay. It's quite familiar. So it has two parts: when the current is increasing, when current remains constant. So we already seen this thing. We have already seen this thing for MOSFET. So we can have two regions. On the left hand side, when the current is increasing, we call it saturation. And the right hand side, when current remains constant, that is our active region. Okay. So for saturation, VCB is greater than minus 0.7 volt less than, okay, minus 0.4 volt. This is the range for saturation. So this is the range for saturation. And for active, VCB minus 0.4 volt. 0.4 volt. Okay. So that's the thing that we mostly covered in our last class. Now we are going to now we know that we already learned that the BJT has 4 region of operation. So they are saturation region, forward active or active region, and cutoff region. What is the cutoff region? From there I can find out the cutoff region. So let's find the cutoff region. Cutoff region is when current is 0. So when all the current IB, let's say, so IC is 0. So let's IC is 0. IC is 0. So IC is 0 means all the current is in fact 0. So cutoff region. And we found out when both the junction is reversed by. So now how are we going to determine? So what are the statement we can write? What are the conditions that must satisfy for the BJT to be operating either in saturation region or in active region or in cutoff region or in forward active regions? So let's find out the general statement. Okay, for that I need to know the BJT. So BJT. Okay, I think now I can follow this. Okay, BJT voltage. Okay. So we have this NPN BJT, and this NPN BJT, we have a 3 terminal: base terminal, collector terminal, emitter terminal, or base node voltage, collector node voltage, or emitter node voltage. Base terminal voltage we call it VB, collector terminal voltage we call it VC, and the emitter terminal voltage we call it VE. And from your DC circuit concept, the node voltage or terminal voltage means any voltage that is measured with respect to ground or any reference point. So when I say VB, it as if with respect to ground, this terminal voltage is measured VB. When I say VC, terminal or node voltage, so with respect to the ground or reference, the collector terminal voltage between these two nodes is VC, and similarly VE. So these are the terminal voltage or the node voltage. And also we can measure voltage between base and emitter, between base and collector, between collector and emitter. So let's say we put the notation such that between base and emitter we call it VBE, between collector and base we call it VCB, and between collector and emitter we call it VCE. Okay, and the polarity sign is given this way. So in that case, if we apply KVL, we find the summation of all the voltage around a loop must be 0. So that gives us VBE plus VCB equals to what? VCE. VCE. And then if we use our 2-diode model, okay, so like this one, okay, and we want to find out the condition for active region. So let's say for active region, want to find the condition for active. So EBJ must be what? EBJ must be forward biased. One of the thing is that EBJ must be forward biased. Okay, if emitter to base junction is forward biased, what can you do? We can replace the, okay, I don't need these things for, okay, we can replace the BJT with what? Can replace the BJT? A DC voltage source of 0.7. since it is diode and forward biased, 0.7. So what is VB? VB is equal to, in fact, 0.7. So I can write VB 0.7 plus VCB equals to VCE. So in fact, what is it? VCE is what? Equal to VCB plus 0.7. তার মানে হচ্ছে, if you know VCB, if you know somehow we can determine VCB, and then with that you multiply, add 0.7, you get the value of VCE. Okay. So just now, what you learn? What is the condition for the BJT to be operating in active region? VCB must be greater than, this is the equation. Then we find VCE must be greater than minus 0.4 plus 0.7, which is 0.3. So that is the condition. So you can say, what are the, so write down. So let me write down. I have this thing in summary. I can borrow it from there. Okay. So condition for the BGT, the condition for an NPN BGT in active region, first of all, emitter to base junction must be forward biased. Therefore, VB is equal to 0.7 volt. And then VCB must be greater than minus 0.4 volt, or VC must be greater than 0.3 volt. So these are the conditions. If these two conditions are satisfied, first of all, you need to satisfy condition 1. Once the first condition is satisfied, then if either of these condition is satisfied, either VCB greater than minus 0.4 volt or VC greater than 0 volt, then you can say the BJT is operating in active region. Then what is the condition for saturation region? So saturation region. Of course, for saturation region, first of all, emitter to base junction must be forward biased. This is the first thing first. Okay. Condition 1. This is the thing. So that means VBE must be 0.7 volt. Now, what about the VCB? So notice here the condition for the BJT to operate in the saturation region, range, it is presented as a range. VCB has to be greater than minus 0.7 volt or less than when current is increasing, collector current in that case, so that is our saturation region. So, and it occurs between minus 0.7 volt to minus 0.4 volt for VCB. Now, since the range is very low, you see what is the range? Roughly 0.3 volt. Okay. So 0.3 volt. So what is customary? Instead of going for a range, they say, okay, we just make it simple. We call it VCB is equal to minus 0.5 volt. We're going to they consider in such way, consider fixed value instead of going through a range of very small range, 0.3 volt, minus 0.7 to minus 0.4. So they just consider a fixed value. Of course, some book they consider minus 0.7, minus 0.5. Books to books they you know they vary it. The same way, the argument is same. We know that when the diode is forward biased, diode can have different value. In reality, you will find different value, and you have already um, observed this thing in your lab. So it could be 0.63, 0.65, depending on the diode, it could vary. But end of the day, we everyone agreed, instead of going through numerous values of very narrow range, we just call it 0.7. Similarly, they call it, okay, VCB is 0.5 volt when it is saturation region. Okay, if this is the case, then according to this relationship, using this relationship, what is should be the value of VCE? So if you plug the value of VCB, so that comes VCE equals to minus 0.5 plus, that is 0.2 volt. So what is the conditions? If I summarize the condition, after this, if I summarize the condition for saturation, this is the summary. So summary say, for the BJT to operate in the saturation region, of course, VB must be 0.7 volt and VCB either must be minus 0.5 volt or VCB 0.3 volt. Okay. Any question? No. Compare this thing with with, so let's say, for active region. So just write down the, just write it down, this part. Okay, active region. Let's make in comparison. Okay, for both case, this must be satisfied. For both case, at least this is common. VBA equal to, then for saturation region, and it's active. Notice the difference. For saturation region and active region, VCB and VCA, both of them are fixed value. Minus 0.5, minus 0.0, minus 0.5, and VC 0, fixed value. On the other hand, for active region, it is what? It's a range. It's a range, not fixed. Which means it becomes a variable. So that's the difference. In the active region, it's a range. We any value greater than minus VCB, greater than minus 0.4. If it is 0, it satisfies the condition that it is greater than minus 0.4. It is 5, 6, 10, all of them active region. But whereas in saturation is fixed value. So remember this, for saturation region, VCB and VC are fixed value. For active region, VCB and VC are range. Okay. Now we present the same thing for PNP BJT. For PNP BJT, if we do the same thing. All right. So in that case, I just simply okay. So we draw the circuit as a PNP BJT. P type, PNP emitter, base, collector. Okay, so the emitter, this is our VE, VB, VC. The voltage between emitter to base VEB, and it is higher potential. This is lower potential as if we make it forward bias. So, and P side is connected to the positive terminal, N side is connected to the negative terminal. So make emitter to base junction forward bias. On the other hand, collector to base junction, we made it reverse bias. It is an arbitrary selection. We call it VBC. N side is connected to the positive terminal and P side is connected to the negative terminal, and we do it VCE, okay, VEC. So that means you notice that things are flipped. So for NPN it was VBE, PNP it becomes VEB. For NPN it was VCB, for PNP it becomes VCB. For NPN it was VCE, for PNP it is VEC. So if you do that again, that KVL, so VEB plus VBC equal to VEC. Again, emitter to base junction forward biased. If it is forward biased, we can write it as 0.7 plus VBC equals to VEC. Okay, so that means this is how VEC and VBC are related. VEC is equal to VBC plus 0.7. So then what is the condition? So I'm just since these are the same things, I'm just going to write down the condition for the BJT operating in active region or in saturation region. Active region, EBG must be forward biased, and number one condition, VEB must be forward and VEB 0.7, and VBC must be greater than 0.4 volt, or VEC must be greater than 0. Again, it's a range, not fixed. For saturation region, emitter to base junction must be forward biased, and VEB 0.7, VBC minus 0.5 volt, and VEC 0.2. Again, fixed volt, fixed. Okay, so these are the condition for the BJT to be operating in active region or in saturation region for both NPN BJT and PNP. Of course, you would say, what about the cutoff region? So that's a cutoff region. We know that in that case, both the diodes are reverse bias. EBJ reverse bias, EBJ, CBJ reverse bias. But generally, if it is EBJ reverse bias, that is enough for us to say. In that case, we're going to find no current flow. So IB equals to IC equal to IE. All of them are 0. All of them are 0. Okay. So next topic is BJT characteristics. IV characteristics and also BJT configuration. Okay. Okay. So what is IV characteristics? In electronics term, IV characteristics mean finding the relationship between the current that flows through the device and the corresponding voltage across the device. And this is the thing we have been hearing it from the diode. So ID versus VD. And for MOSFET, it was ID versus drain current versus VDS, drain current versus VGS. For example, if you consider a diode, so let's say we have got a diode. And the current through the diode is ID. The voltage across the diode is VD. And then we know that what is the IV relationship? IV characteristics is finding the relationship between ID versus VD. So in that case, we found out it is like this: ID versus VD. And if it is forward biased, that gives you an exponential relationship. Okay. But what about diodes or BJT? So let's say for BJT, okay, let's if you have a BJT which has 3 terminal: base, collector, emitter. Each terminal we have got one current: base current, collector current, emitter current. Now also between each terminal we have one voltage: VBE, VCB, VC. So we have 3 current, 3 voltage. So which means that if I am to find the relationship between current versus voltage, the obvious question is that which current and which voltage. For example, if I take IB, so let's say if I take IB, and one possibility is IB versus what? It could be VBE, okay, or it could be VCB, or it could be VCE. So I can make a relationship between IB and VBE, between IB and VCB, between IB and VC. That could be one possibility. Or I can do the same. So I have this thing there. So I'm just copy it from there like this. It could be like this. It will be IC versus VBE, IC versus VCB, IC versus VE. Similarly, IE versus VBE, IE versus VC, IC. So there are 9 possible combination of IV characteristics. So it gets clumsy. So how exactly which relationship is important for us? And that's the one important. So how to how is that possible to make it a discipline? One way is that they say, first of all, let's see how we use the BJT to build an amplifier. If you are actually, we know that main purpose of a BJT, main application of BJT is to use as an amplifier. Okay. If I want to use it as an amplifier, and that is true also for MOSFET. How are we going to connect the device, either BJT or MOSFET, into the circuit? So this way, they came up with 3 types of configuration. They are called BJT configurations. The first one is called common base configuration. What does that mean? So let's say we have an amplifier inside this box. I've got this box, black box. So right now we don't know what we have inside. We may have different things. Well, all we know that we have got some input signal, input port where we apply the signal VI input, and we have got output port from which we take our output. So input and output, input applied, output we obtained, it amplified. Now the question is, how are you going to place the BJT into the amplifier? So in common base configuration, the BJT is placed such that, okay, so let's say BJT is placed such that if the emitter terminal, sorry, base terminals common to both input like this. So like, let me draw it fast. So let's say In addition to many other things, we have got the BJT inside this box, and it is connected this way. What does that mean? You notice this is our base, this is our emitter terminal, and this is our collector terminal. Okay. Notice the base terminal is common to both input side and also to the output side. If this is how the circuit is, the BJT is connected, then this configuration is known as common base configuration. Again, if the base terminal is common to both input side and to the output side, this configuration is known as common base configuration. Notice emitter terminal is connected to the input, collector terminal is connected to the output. Only the base terminal is common to both input side to the output side. This configuration is common base configuration. So we could have the same thing, if it is in MOSFET, it could be common gate configuration. Gate terminal is common to both input side to the output side. Common source term configuration, common drain configuration. Now in the input side, we have a input current, which is our emitter current, and input voltage, which is our VBE. Then in the output side, we have our collector current as output current and VCB output voltage. So that means we have two types of characteristics: the input characteristics, finding the relationship IE versus VBE, and output characteristics, that is our IC versus VCB. Input characteristics, you already know, it should be like this. This is our input characteristics. Okay. So these are input characteristics. Because you know how are they related? IE is equal to what? IE is proportional to e to the power VT. So that gives us input characteristics. So as you are changing VB, we get different values of emitter current, which is a diode characteristics. Now, obtaining the output characteristics bit different. So for that, you have to conduct an experiment. So let me, what I'm going to do, I'm going to copy it and paste it here. Okay. I don't need this trimming the waste. And what I'm going to do, I'm going to, so let's say, connect a emitter here. I'm going to conduct an experiment where I'm going to connect an emitter here to connect, measure the current, and then we're going to change the VCB. Okay, before doing this experiment, that means I'm going to change VCB. Every time I change VCB, I'm going to change, I'm going to measure the current. Before doing so, I am going to do one thing. I'm going to take care, I have to take care of the input side. So how are we going to take care of the input side? Set IE, set VBE to a fixed value, so that we get IE, okay, so 1 milliampere, say. Let's say 1 milliampere, say. And okay, so 1 milliampere. So I do what I somehow I just tune the VB so that I get IE is equal to 1 milliampere, and so I'll keep it and keep 1 milliampere. We are not going to change. And then what I'm going to do, I'm going to, now I keep IE fixed, and then I'm going to change VCB. So as you are changing VCB, I'm going to measure the current. So all you're going to find, it will look like this. This is what you're going to find, something like this. So let me draw it again. Yeah. So if it, so, and you are going to IC IC versus VCB, and you're going to find something like this. This is minus 0.4 volt minus 0.7 volt. We already found out it should be something like this. Okay, and just it's an approximate. Okay, so let's say this is our 1 milliampere IC, and that is our 2 milliampere. This is 3 milliampere. Mark that 0. Let's say this is our 5 volt. This is our 10 volt. This is 15 volt. So you see, that's what you're going to find. The current is constant, and then so that's what I'm going to do. I change IE to 2 milliampere. Let's say to next I set IE is equal to 2 milliampere, and we run the same experiments. In that again, we're going to find something like this. Okay? They're going to find something like this. Just for 2 milliampere. Again, if I set IE to 3 milliampere, then it will be like this. You see what? You got a series of curve, family of curve. So this one is for I is equal to 1, then this was I is equal to 2, and this 3. So I can write it down. So that was the bottom one. I can label it when I is equal to 1 milliampere. Then was I is equal to 2 milliampere, and this one I is equal to 3 milliampere, and so on. So that means this is the relationship between collector current and collector for different values of I. For example, if I pick one point here, let's say on the curve. So what information we get? Information we get, okay, let's call it Q1. We get two value, IC and VCB. We can find so Q1. So if I set Q1, you can say IC is, let's say it's 1. It's 1. Let's say it's 0.9. Let's say 0.9 milliampere. And then VCB, you read it is 5 volt. Let's say take another point here. Okay, so Q2. For Q2, okay, you can say IC is equal to what? Same 0.9. Current doesn't change. But VCB, okay, VCV is what? VCV is equal to, let's say, 10 volt. But at the same time, we get another information. While in both case, I is equal to what? 1 milliampere. Now, similarly, if I pick another point here, let's say Q3, we can get what? So Q3, we get, first of all, IC is equal to koto? Let's say 2.7. So 2. And VCV is equal to, let's say, 7.5. And also what? It means I is equal to 3 milliampere. Let's say if I take one point here. So in that case, you see current changing. So it for it gets, let's say, Q4. So Q4, Q4, Q4. You can say, let's say minus 0. Minus 1.8 or 1.6. I see 1.6 milliampere, and VCB minus 0.6 volt, and I is equal to 3 milliampere. So in fact, it's operating in saturation zone. Okay. So that is our common base configuration. So next, our common emitter configuration. So common as the name suggests, if the emitter terminal is common to both input side and to the output side, this configuration is known as common emitter configuration. Let me draw it. How does it look like? Okay. So that is our base, emitter, collector. This is where the input is Vi. This is where the output is V0. You see, the emitter terminal is now common to both input side and the output side. Base terminal is common to input side and the collector is common to output side. This configuration is common emitter configuration. Again, it has two. Okay, one thing I forgot to mention. So let me just put it down. Yeah, in common base configuration, if you notice what is the output current, IC, what is the input current, IE. So we can easily find the gain or amplification, amount of amplification, current amplification or gain is as IC over IE, output over it. That is termed as alpha, which is known as common base current gain or amplification. ঠিক আছে? Or this, I guess I don't need this. Okay. In common emitter configuration, again, what is our input current? IB. Input voltage, VB in. Output current, IC. Output voltage, VCE. Okay. So input characteristics, IB versus VBE, and the IB characteristics look like this. I can just okay. So IB versus VBE. How about the output characteristics? Output characteristics, IC versus VCE. IC versus VCE. So for that, what should we do? We're going to conduct the same types of experiment as we did before. First of all, in fact, this is the experiment we are going to do. First of all, what you're going to do, you are going to set base current. The previous case, we set the emitter current fix. Now we're going to set base current fix and then change VCE. So every time we change VCE, we're going to measure the current flowing through the collector terminal, and we're going to get IC versus VC curve. Now, there is a very straightforward way to obtain this relationship. Remember the relationship we found out that VCE is in fact VCB plus 0.7. So that means with VCB, if you add 0.7, you get VCE. So that means if you look at this IV characteristics, IC versus VCE, in both case, and IC versus VCE. So in horizontal or the vertical axis, current remain the fixed. Only thing that we have changed with the horizontal thing. So like this, let's say I just copied this. And paste it here. Okay. So that is trim it, trim the unwanted bit. Okay. It is. Okay. And okay. So put them side by side. Okay. Net. Okay. Now notice on the left hand side, it is IC versus VCB. The right hand side, we have IC versus VCE. Let's call it VCE. I want to transform this curve to IC versus VCE. What should I do? I'm going to operate on the x-axis. So you notice if I add VCB with 0.7, so we get VC. So simply, if I add, okay, so we have this. So if I add 0.7 with minus 0.7, that gives us 0. So that means this point, starting point will become 0. So all I'm going to do, I'm just copy that bit and shift it here. So that will become minus 0.7 will become 0. So that will become 0. Minus 0.7, minus 0.4 will become minus 0.4 plus 0.7, it will become 0.3, and everything will be shifted as there. So that is our curve. So curve will remain identical. Only thing is that for IC versus VC curve, the starting point will be shifted. Otherwise, current, because the vertical axis remains the same. And here it is for IB. Let's say IB, because since we are IB is equal, let's say 15 microampere, and that one is IB is equal to, let's say 30 microampere, and for IB is equal to 45 microampere, and so on. So that is how we can find out. So any point on the curve that gives us the value of base current, value of collector current, and value of collector to emitter voltage. So that is, if we add entire thing plus 0.7, we get this. And in that common emitter configuration, output current is IC, input current is IB. So the ratio IC over IB is known as beta. It is called common emitter current gain or amplification. How much amplification of the currents are taking place in common emitter configuration. So that is our common base configuration, common emitter configuration. We have one more configuration, which is common collector configuration. So right now it is not that important, so we're going to skip it for the time being. When it is required, I think we can discuss about it. Okay. So next we're going to find out the BJT current. So how to relate BJT current? So BJT. Already we know that BJT has three current: IB, IC, and IE. And the general relationship, regardless the type of BJT, whether it is NPN BJT or PNP BJT, it is always, and the BJT operating in active region or saturation region or in cutoff region, this is universal relationship, is that IE equals to IC plus IB. Whether it's NPN, PNP, active, saturation, cutoff. In all case, this is true. Now, what is the relationship between? Now, next I'm going to find active region. So, current in active region. If the BJT is operating in the active region, in that case, in addition to this relationship, I can already found out two more relationship. Number one, alpha IC over IB, IE, and beta IC over IB. So using this, and alpha and beta, I said this is alpha and beta, it's a BJT parameters. Is a BJT parameters. Okay, every BJT has its own beta value and alpha value. As a BJT parameter, so known, it can be determined or given. Okay, right. So using this, so that means I can somehow find out the value of alpha, I can somehow find the value of beta. So for active region, I can write what? IC is equal to what? IC is equal to beta IB, or IC is equal to alpha IE. Now I'm going to do, school level maths. So you're going to find out using this and using this relationship, you can find IE equals to 1 plus beta IB. Also, you can relate alpha and beta. Alpha is equal to beta over 1 plus beta, and beta is equal to alpha over 1 minus alpha. It's all school level mathematical relationship. So important thing to remember. So again, as I also mentioned, it's already been mentioned that you are allowed to use alpha and beta to determine the current as long as the BJT is operating in actives. Alpha beta is allowed. Alpha beta allowed only for active region. In saturation region, if the BJT is operating saturation, alpha, beta not allowed. You're not allowed to use alpha and beta. মনে রাখতে হবেই হবে. So then how we can determine the current, we can learn later. Acha, let's go for an example. Let's say for a particular BJT operating in active region, we have emitter current is 1 milliampere and alpha is equal to 0.99. So what do you have to determine? I have to do, given these two information, I have to determine the base current, I have to determine the collector current. Also, I have to determine the base current. So what are the things? So first of all, what are the known things? IE, alpha, IB, IC. So what are the unknown things? IB, IC, and what are the information you know? Or the things known? We know that, okay, first of all, we determine beta. Beta is equal to 0.99 divided by 1.0.1 minus 0.99. So roughly gives you 100. Okay. And then if I know beta, then I can determine IB as IE divided by 1 plus beta, which gives us 1 divided by 101. And then IC as beta IB. Okay. So 100 times 1 divided by 101 milliampere. So that is how we can determine. So that means between 5 terms, so IB, IC, IE, alpha, and beta are in fact synonymous, because if you know alpha, you can determine beta. If you know beta, so 4 terms. If you know at least one current component below of the alpha and beta, or 2 current components, then it is possible for you to determine all the other parameter. For example, you know IB and IC, then you can determine beta. You know IC and IE, then you can determine alpha. Then you can determine all the other current component. Okay, or you know IC and alpha, you can determine other parameters. ঠিক আছে? Again, keep that in mind. You are not allowed to use alpha and beta if the BJT is operating in saturation region. Now we're going to conduct an exercise to check if the BJT is operating in active region or in saturation region or in cutoff region. So let's say I've got a BJT and the terminal voltages are known. So this is our BJT. Okay. So let's say this BJT, the base terminal voltage is 3 volt, and emitter terminal voltage is 2 volt, and the collector terminal voltage is, let's say, 1 volt. So given the base terminal voltage, emitter terminal voltage, and the collector terminal voltage, I need to find out which region the BJT is operating, either operating in active region or in saturation region or in cutoff region or in reverse active region in that case. Okay. So first of all, we can do one thing, draw the 2 diode model of the BJT. So it's our EBJ, that's our CBJ, emitter 2 volt, collect base 3 volt, it is 1 volt. So we have 2 junction, all we need to do to check if the BJT is operating in any of this region, we need to go for first check EBJ. For that, we do VBE or VEB, either way. So VB minus VE. VB হচ্ছে 3 minus 2, 1 volt. So all I can say, well, VB at 1 volt means base is bigger than E by 1 volt. Base terminal voltage is bigger than emitter terminal voltage by 1 volt. So next question is that what types of material the base is and the what types of material the emitter is. Okay, so base is our P type metal, emitter is our N type metal. So P is bigger than by 1 volt, it's clearly greater than 0.7 volt. So that makes it is forward bias. So I can say emitter to base junction, forward bias. So is that enough? No, it's not enough. So I need to do check EBJ. So let's check EBJ. So check CBJ. Again, we do VCB or VBC JT coordinate. So VC minus VB. VC হচ্ছে কত আমাদের 1 volt, VB হচ্ছে 3 volt. So 1 minus 3 minus 2 volt. So you can say C is less than B by 2 volt. Collector terminal voltage is less than base terminal by 2 volt, minus 2 though. So next check what types of metal. It is our N type metal. What types of metal the base is P type metal. তার মানে হচ্ছে N is bigger, smaller than by 2 volt, or P is bigger than N by 2 volt, which is clearly greater than 0.7 volt. So that means CBJ is also forward biased. So EBJ forward bias, also CBJ forward bias. তাহলে কোন রিজনে কাজ করছে? So BJT is operating in the BJT is operating in saturation region. So let's do another example. So in that case, we do PNP BJT. I think I have it. I just borrow it from here. Okay. So a PNP BJT, base 3 volt, collector terminal voltage 5, and the emitter. So again, EBJ 2 volt, 3 volt, 5 volt. So check EBJ. So VE minus VB. VE হচ্ছে আমাদের 2 minus 3 minus 1. So E is less than B by 1. E is our P type material, B is our N type material. So it's the reverse bias. Emitter is basically reverse bias. Similarly, check CBJ. So we do VCB, VC minus VB. VC হচ্ছে 3, VC হচ্ছে 5, and VB হচ্ছে 3. So C is C VCB 5 minus 5 minus, sorry, minus 5 minus 5 minus 3. Okay. VCB 5 minus 3. C হচ্ছে আমাদের P type material and B হচ্ছে আমাদের N type material. So clearly P is bigger than N. Okay. By 2 volt. So that gives us so forward biased. Forward biased. Yeah, it's forward biased. It should be forward biased. It's forward biased. Forward biased. So collector to base junction forward bias, emitter to base junction reverse bias. What types of, which region is that? We already learned this is a reverse active. So that means it's possible for you to determine the region of operation if you know all the terminal voltage of BJT. Any question?
স্যার রিয়েল লাইফ কেস সিনারিও থেকে আমরা রিভার্স অ্যাক্টিভ বায়াসটা দেখি মানে রিজিয়নটা
Sorry.
রিয়েল লাইফ সিনারিওতে কি স্যার আমরা রিভার্স অ্যাক্টিভ রিজিয়নটা দেখি
No. Reverse. No, actually, reverse. It's not designed. The BJT is not manufactured or designed to operate in the reverse active region. এর কোনো অ্যাপ্লিকেশন নেই।
স্যার আপনি বিজেটি কনফিগারেশন যেগুলো বললেন এগুলো তো সব স্যার অ্যাম্পলিফায়ার বেসড না
No, amplifier is the general configuration. There actually do no such thing as amplifier based configuration, or it is when I draw the configuration, it is as if I am considering is amplifier, but the characteristic is a general characteristic. When you look at the characteristic, it's a good question. Okay, when you look at the characterization, maybe I obtain these things considering it is an it is, but notice, you see the IV characteristics, it has, so this part, this region, we have got saturation region here, right? So it includes everything. So it's a saturation region. So this side is our saturation region. This is our active region. And this is when the current is zero, cutoff region. Okay. Although we obtain this thing just configured in such a way, but when you conduct the experiment, it includes saturation, it includes active, and includes cutoff. So IV characteristics is it shows everything. ঠিক আছে? But when it, yeah, you are in a way, when it comes to the configuration, yeah, I drew it as if it is it is amplifier. But from there, whatever the characteristics we obtained, it's general. ঠিক আছে? আর কিছু কার কোনো কোশ্চেন আছে? Okay. So I'm going to call you for the attendance. So you just respond very quickly. I'm going to wait for a while, but I'm not, and then continue. So in case anyone misses it, so you'll miss your attendance. Riazul Jannat.
প্রেজেন্ট স্যার